about downscaling and why we use it. And I just want to give a really recent example of the benefits of it. We had a lake effect snowfall event just a few days ago that struck the Lake Michigan shoreline. And you can see here the totals right around Racine and Kenosha County. Some places got a foot or so of snow over just a few hours, but notice how much of a gradient there is. You go to from Racine along the lakeshore, you go inland just a few miles, and there was nothing, nada. And so this is typical of lake effect snow, and it's an example of how you can't use global climate models to try to simulate that process. And one problem that the climate models have at the global scale is that they typically don't resolve the Great Lakes very well. Even if they did, they don't have the necessary detailed physics to capture the local effects, the physics that are responsible for lake effect snow. And I'll give you an example here. Large-scale global models are really good at the big picture, as Michael said. And we know the big picture ingredients that are responsible for lake effect snow. You need cold air, you need warm lake water, you need ice-free conditions, and you need a strong wind blowing over the lake. And so those large-scale factors are called predictors, listed here. We can get those from a large-scale climate model or gridded observational reanalyses. What we want to know, though, is the local conditions, the snowfall, the predictand. And so here's just a schematic of lake effect snow forming. You got a picture of the, a sense of the big scale predictors and then the small scale outputs that you want. I'm going to show here a few popular statistical downscaling products that you might hear about. It's an alphabet soup. I apologize here. One of them you might hear about is called MACA, M-A-C-A. Another one is LOCA. These are two analog types of products. Another one is the UWPD, which I'll get into next. But let me first start off with MACA and LOCA. So these are downscaled products, just a moment, that rely on historical analogs. So you look for a set of days or a single day in the observational record that resembles the GCM output or a reanalysis output, we'll say. So that's MACA. LOCA would be a single day, so very much analogous. Now, the UWPD is a very different type of process. So it's based on probabilistic relationships, not strict linear regression or analogs. And it was developed in-house by our very own CCR's Dave Lorenz, who some of you know. And one of the things that it does that's different is that it allows a variety of weather conditions to be chosen from the same large-scale weather pattern. And this is realistic. So we know when the conditions are right for severe weather, for example, some days it happens and other days it doesn't. It makes forecasting difficult, but that's the stochastic nature of the atmosphere. And so that's something that UWPD provides that the other methods don't. Now today I'm going to be providing a real Cliff's Notes version of the UWPD. But if you want the full novel, I recommend contacting David Lorenz in our center. There's his email, or you can go to the original source of the journal article from about 10 years ago that has an earlier version of this method and get some of the details. So let me walk you through an example here of typical statistical downscaling procedure, where you have a regional scale predictor, say from a climate model or a reanalysis, meaning a gridded observational data set, and you're trying to find the weather variable of interest, say in this case, the temperature at a weather station. The first step is you determine the statistical relationship between the large scale fields in, say, the reanalysis and a weather station of interest, say one of those weather stations in Racine County. You also need to debias a climate model if you're using one so that it looks like reanalysis or observations. Some climate models have systematic warm or cold biases, wet or dry biases. You need to correct for that. And then you apply the statistical relationship in this step number 1 to your climate model. So if in a simple world, a perfect world, you'd have this kind of relationship, a very linear relationship that when you have, say, 10 degrees from your regional, your global model or your regional, your reanalysis, you would then just kind of do a lookup table and say, okay, so that corresponds to a 9-degree temperature at my station of interest. But the world is not that simple. There's a lot of noise that complicates this simple linear relationship. But that is the small scale temperature variability, and we want to preserve it. But exactly how you account for it, just a simple kind of normal distribution of the noise, is not known for certain. And Gaussian estimate is pretty good for the most part, except when we get into the issue of extremes. But basically, for a variable like temperature, the statistical downscaling is easier. For precipitation, it's more complicated. And so the way it works, these slides hereafter are provided by Dave Lorenz, describing how you downscale precipitation at a station. So, for instance, precipitation is not at all a simple linear relationship. It's much more of a steep drop-off. It's an example for Madison. The precipitation amount corresponding to Madison, and then this is the frequency in the historical record. So not surprisingly, we have a lot of dry days or a lot of days with very little precipitation in Madison. We have some days with a lot, but not very many. And so the way that Dave treats this is to do a two-step procedure. The first step is to create a model for precipitation occurrence. Simply put, is the day wet or dry? The second step is to calculate the precipitation amount if the day is wet. And the probabilities of these are determined, the amounts are determined from these large scale predictors I'll describe next. So first, the precipitation occurrence model. The precipitation occurrence can take on two values. It's either dry or it's wet. And so the goal is to predict the probability, this P of T, that a certain day is wet. And you do that based on the large scale predictors from either your reanalysis or a climate model. And the way Dave treats it is just to have a kind of a off to the side generation of random numbers between 0 and 1, this R of T. And based on these large scale predictors that you're using, is the probability of rain or snow greater than that random seed? If it is, the day is considered wet. Otherwise, the day is considered dry. Now, for precipitation amount, it gets more complicated. For this, Dave uses a generalized exponential distribution that is the statistical distribution that corresponds to what he finds is most accurate. It's similar to a gamma distribution, if you're familiar with it. And so the way it works is that you have this relationship, probability here, P, and then the rainfall precipitation amount. And you fit a distribution that has these two parameters, A and B, a shape and a scale parameter. And these are functions of the large scale predictors. So for example, maybe the reanalysis or your climate model is suggesting that a location is wet, really humid, winds blowing right off the Gulf of Mexico and so forth, all conditions favorable for heavy rainfall. And so that would affect how the choice or the value of A and B. And so here's some examples for different values of A, for example, in this equation. It can look like a steep drop-off in the red. It can look like a typical exponential drop-off in green, or it can look like the blue and purple, where you're going to peak here somewhere between, say, ½ an inch and an inch of rainfall. So it all depends on the conditions for a given day, what those parameters are, and therefore what kind of shape your distribution looks like. And here's a nice example of the method at work. This is for Madison. This is showing the example of the PDFs that work, those being in red here for 17 days in February of 2019, just by chance. I just selected a month at random. And the station is right at the UW Arboretum. So here's the 8th of February down to the 24th. The blue bars represent the observed precipitation down at the bottom here in millimeters. So some days were wet, some days were dry. And you can see on the right the probability of precipitation from the PDFs or from the downscaling assumptions. Sometimes it's very, very high, like on the 12th of February, 99% probability. And sure enough, it did rain or snow that day. Other days, very low probability. It ended up dry. But one of the things, if you look carefully at this, you'll see some examples like on the 17th and the 18th of February. Uh, Probability of precipitation was about 50-50 on the 17th, and yet there was a actual precipitation amount. The probability of precipitation was much higher the following day, but not quite as much rain or snow fell. And that is an example of how this UWPD takes into account the stochastic nature of climate and weather. Going to show you an example here of the ability or inability of statistical downscaling to capture extreme precipitation. I mean, if you're in the infrastructure working group, you care about this a lot, and you care about how well it's represented. So I'm going to show you here an example of simulation or downscaling from LOCA, one of the methods I mentioned before at the outset, and compare it to observations of a 20-year event. So this is a 1 in 20-year rainfall, 24 hours duration. So it's a pretty hefty storm. And when we look at an observed gridded data set up here at the top, this is the distribution across the country. The greener values in blue indicate heavier amounts of precipitation for that 24-hour precipitation, the brown lighter amounts. So not surprising when you're near the Gulf, you get high amounts. As you get further north, it gets smaller and smaller, but you still see the Gulf influence here, also along the eastern seaboard. But when you're out west, these are very low values because of the dry climate. But overall, there's a 98 millimeters per day across all the stations in the US. But at the bottom here are the two LOCA examples. And you see at the outset that just averaged over the whole country, these are much lower than the observational data. And if you just eyeball it, you see a whole lot more brown on these maps, right? Compared with the observations, which show a clear influence of Gulf moisture going north and providing fuel for heavy precipitation. And as I note here, weak precipitation extremes are a common problem with most statistical downscaling products that I'm familiar with, LOCA included. And part of it is because of their very construction of using analogs. If you pick the average of, say, 30 best days, you necessarily won't pick the very highest day of precipitation. And so this is one of the shortcomings. By contrast, this UWPD is really beneficial because, because it has a different approach. So as I said, it uses these PDFs in the equation for precipitation amount. That's fundamentally different than the LOCA or the MACA construction. And so the UWPD approach, again, you calculate the PDFs to determine individual parameters in the precipitation amount equation at individual stations. And then Dave interpolates these PDF parameters between stations to estimate the precipitation elsewhere in between those stations. And when you do that, or when you look at the outcome of that, you see here, this is the UWPD version of these 20-year, 24-hour duration storms, and they look extremely good compared with observations. They definitely capture the Gulf influence, the eastern seaboard, very much like observations, and much superior to the LOCA results. Now I'll give an example for a specific day. This is one that Dave just picked randomly using the newer CMIP 6 global climate models. There's 28 that have been downscaled and that'll be used in the wiki report coming up, and 4 different future greenhouse gas emission scenarios. The example showing here is from one called the Access Global Climate Model, and showing 3 different realizations. So that's the benefit, again, of the PDF. You can construct multiple, infinite possibilities of small scale temperature or precipitation for the same large scale predictor field, the same large scale weather pattern. What we find here is that the climate model precipitation from this particular GCM is shown here. On this day, there was a lot of rainfall near the Gulf, and then a lot of rainfall in the northern plains. The 3 random realizations, number 1, it captures things in a general sense. It captures these 2 bullseyes, one south and one north, but the northern bullseye is situated over Minnesota instead of more over the Dakotas. And then this surge from the Gulf goes farther north than it did in the climate model. Realization 2 looks quite different. It doesn't capture nearly as much of the precipitation, the heavy rainfall near the Gulf, and it produces a heavier precipitation amount all the way down into Nebraska. But random realization number 3 looks awfully like the original, the climate model precipitation, but much more fine scale. You see this detail here in Louisiana and Texas that you don't get in the coarse GCM. And for reference, this is the probability of precipitation according to the downscaled approach. So you see the 2 bullseyes. And then if it's a wet day, this is the mean precipitation from the downscaling. And then my final slide before I hand it over to Michael is showing the new results for the future climate. This is something we all care about in the wiki community. How is our rainfall, extreme rainfall, likely to change in the coming decades? And for this, I show from Dave's recent seminar that he presented the change in mean precipitation over the 28 CMIP6 climate models he downscaled for the late century. This is the 2070s to 2100 versus the reference period from 1981 to 2010. And this is for a high greenhouse gas emissions scenario. The months are clustered in pairs. So you see January, February here at the top, March, April, and so on. The big takeaways here at the bottom, we're expecting wetter winters, springs, and falls in Wisconsin. And that's the same story we've been harping on for years, but drier summers in these newer runs of models. I'll walk you through it here. January, February, all this green indicates wetter than the reference period. Here's the scale at the bottom. March, April, springs continue to be wetter in the future, according to the projections. Still wetter slightly in May, June, but look at July and August. In the thick of summer, the newer round of climate models are suggesting we could be seeing a 10, 20, 30% drop in summer rainfall in those 2 months, which would really be impactful. But by the time we get into the fall here, September, October, a bit wetter than present, and then even more so in November and December. So this is kind of the big takeaway in terms of the future, but it also gives a picture for you in terms of the under the hood contents that go into the statistical downscaling results. So Michael, I will now hand it back to you.
Thank you, Steve.
We'll go for the regional models here.
Thank you. So I'll kind of return to some of the discussion about dynamical downscaling and the idea that when you use a regional climate model, it provides added value beyond what the global climate model can provide. Part of that is because of the higher resolution of the regional model, but then also part of it by more advanced physics parameterizations, and ultimately trying to improve the simulated patterns of both mean conditions. Oops. Both mean conditions, but also extremes. With the higher resolution with a regional model, you can have more detailed representation of topography, coastlines, land cover, and their influences on precipitation. Potentially, you can also include a better representation of large lakes, like such as the Great Lakes, if you want to look at lake atmosphere interactions. So next slide, please. The other benefit is really regional climate models typically are better at capturing the magnitude of extremes. For example, heavy rainfall events. Global climate models rely heavily on a cumulus parameterization. They rely heavily on those large scale course predictors. And they really struggle at representing heavy rain events associated with, say, thunderstorms, squall lines, features such as that. Regional climate models, depending on their resolution, can improve representation of vertical motion, of unstable atmospheric conditions, and also coupling between regional circulations and convection, producing more accurate capturing of mesoscale features. Now, with the original climate model, if it's run at a high enough resolution, then you can have convection resolving or convection permitting simulations. If they're run more costly, like say 20 kilometers, they continue to make use of cumulus convection parameterizations. So next slide. So I want to describe a little bit about some of the work going on within CCR. In past years, we worked quite a bit with the Reg CM4 regional climate model, running at a 20 kilometers grid spacing, coupled to a 1D lake model to represent the Great Lakes. That was a great advance in terms of really improving the spatial resolution, but also including lake atmosphere interactions in a way that a global model really was unable to do so. But there was a lot of deficiencies, both of because of the coarseness of the model at 20 kilometers, its reliance on convective parameterization, but also the fact that the 1D lake model really is not optimal for deep lakes, for simulating accurate lake temperature, ice cover, and evaporation, and processes such as stratification of the lakes. So with our new work, we're working with convection permitting simulations, so running more 3 kilometers grid spacing, no longer using convective parameterization, so we're directly simulating those heavy rain events, given that fact that really heavy precipitation is probably the main impact at this point for the Midwest region of climate change. We're also incorporating a 3D lake model instead of a 1D lake model, so we can include circulation, overturning, motion of lake ice, some of those advanced phenomena, and therefore producing a better representation of the lake state. Also, a better representation of lake atmosphere interactions and lake effect precipitation. And by going from a 1D lake model to a 3D lake model, where we have much more accurate simulation of lake surface temperatures, ice cover, over lake sensible and latent heat fluxes and evaporation, and also the local regional climate. Next slide. The specific tool that we are currently using is a NASA Unified Weather Research and Forecasting New WRF regional climate model, that was coupled to the finite volume community ocean model, FVCOM. So this model, the regional model is 3 kilometers. It's run across the Midwest and Great Lakes region, coupled to FVCOM to represent the 3D circulation within the Great Lakes in our region. So next slide. This is an example of the domain we're working with. We have an outer domain covering a big chunk of North America. And then within red is our inner domain, which is being run at 3 kilometers grid spacing within our new WRF simulations. Also with 61 vertical levels in the atmosphere, allowing for more detailed vertical profiles of heat and moisture, for example, and winds. So next slide. And if you zoom in a little closer, this on the left is the representation of the topography or elevation. And then also on the right, for example, oh, you don't need to zoom in anymore. On the right is an example of the structured mesh or unstructured mesh within FVCOM. So ultimately, the grid within FVCOM for the lake model is more detailed in regions where you expect more complex features. For example, for along the lake shores, for example. Next slide.
Something went funny there, Michael, with the zoom in. So I may have to
Oh, sorry about that.
get out of it here. How's that?
I can't see anything. Sorry.
Oh, hang on. See where we are here.
Yeah, you can go into the next slide then. Thank you, Steve.
Okay.
There we go. So, for example, if you were to look at one of our simulations we did, forced by observations reanalysis during November 2014 to March 2015, we could see the seasonal evolution of lake temperature on each of the Great Lakes and also ice cover. And the main story is with FVCOM coupled to New WRF, this new simulations, they really nailed a seasonal evolution of cold season lake temperatures and ice cover evolution of the Great Lakes. They're not perfect, but compared to a 1D lake model, it's much greater in performance. The 1D lake models typically have very large temperature biases, produce way too much ice cover, and that can really affect the seasonality of evaporation. So overall, it performs real well in our region. So next slide. And then, for example, if you would look at specific case studies, so Northern Michigan lake effect snowstorm on the top, simulation, the bottom observations, you can see the banded structure within the model and how it can capture that kind of horizontal banded structure of fingers extending off the Great Lakes with these lake effect snow events. So you can definitely get very fine scale lake effect morphology features that are captured in observations. And next slide. And then you can look at another case study. For example, in this case, we have a lake band that was more parallel to the Great Lakes in the model and the observation. Again, you can capture large intensities of these precipitation events and also reasonable morphologies by writing at high resolution and also providing more reasonable lake conditions of temperature and ice cover and turbulent fluxes. So, next slide. And I'll hand that back over to you, Steve. Thank you, Steve.
Okay, thanks, Michael. So, as Michael said, there's not an inherently better approach to downscaling. These statistical and dynamical strategies each have their strengths and weaknesses. And that's what we've put together here in this table to really launch into the discussion period as well. Michael put this together. I think it's an excellent summary, and I'll walk us through it. In terms of, say, like output, so one of the things about statistical downscaling is that it mainly just provides air temperature and precipitation, which for some purposes is enough. But dynamical downscaling, the regional climate models produce a whole bunch of other variables that you might be interested in. Maybe it's humidity, maybe it's wind, soil moisture, ice cover on lakes, and whatnot. So that is advantage dynamical downscaling. Temporal resolution, statistical downscaling usually is just daily. So you get daily average high, low temperatures, precipitation amounts. Whereas dynamical downscaling is useful if you're interested in sub-daily, hourly storms, storms that happen, flash flood kind of events. And so if you're interested in that, then dynamical downscaling provides more information. In terms of biases, I didn't cover this a lot, but in the statistical downscaling generally debiases the, say, the climate model input against observations as part of the the downscaling process. Regional climate model output still needs to be debiased to observations prior to an application, but ultimately they both are debiased. One of the strengths of statistical downscaling is computational demand. It's very fast. It's low computational demand, especially as computers have sped up. Dynamical downscaling is expensive. It's a slower method, high computational demand. You often need a supercomputer, and it can take a long time to generate individual simulations. In terms of the future envelope of climate, one of the strengths of statistical downscaling is that because it is fast and cheap, you can download or downscale lots of different climate models. And that's useful because climate models don't agree with each other on exactly where we're heading into the future. And so you can get a broad envelope of potential future climates, for example, quantify uncertainty and so forth. Because dynamical downscaling is expensive to run these RCMs, you can only do a limited number of these global climate model downscalings. And you basically you get the resolution, the high spatial resolution, but you can't do as many downscalings because of it. Stationarity. This is something that is a weakness of statistical downscaling in a changing climate because it assumes the processes are stationary between predictors and predictands. So observed relationships between large scale and local climate features will continue into the future. And for example, lake effect snowfall, that may not be a good assumption. We always, when there's a warm lake over or below a cold air mass, you'll have the right ingredients for lake effect snow. But in the past, when the lakes may have been more ice covered than they will be in the future, that will change the relationship between those predictors and predictands. By contrast, dynamical downscaling is really good at handling that. It specifically represents ice cover and lake temperatures. And so in the future, as we get declining ice cover on our lakes, presumably, it will be able to account for that and the impacts that that has on lake effect snow. And then in terms of feedbacks, the statistical downscaling has a limited representation of a lot of land surface feedbacks. Often those are missing from the GCM itself. In terms of soil moisture, vegetation, and so on, that can be a limitation, especially if the climate changes drastically in the future. Whereas with dynamical downscaling, at least it has the potential to handle complex land-atmosphere interactions and combinations of impacts in the future, warming lakes, soils drying out, various topographic features, and so forth. So this is a good takeaway of kind of a scorecard of some of the strengths and weaknesses of both approaches, but you can clearly see it depends on your need, what time scale you're dealing with, what process you're dealing with, and so on, as to which downscaling method is preferable for you. And so with that, that concludes our primary presentation here. And happy to turn it back to you, Austin, however we want to do the Q&A. I don't know if people have put questions in chat. Michael and I can handle whatever's thrown our way and go back and refer to slides as necessary.
That would be great. So I think if you've got some questions, please put them in the chat, or if you'd like to, I think maybe if you raise a hand, I might be able to see it and you'd like to ask the question. I think I'm going to take this moment to ask my question really fast. Over our state, with the newest, with CMIP 6, is there an effort to do, I guess, how many realizations and what's the data availability of the regional climate model output? And is there a way that we'd be able to sift and look at how extremes might be changing? Is that something that you guys are looking at?
So in terms of the dynamical downscaling, the previous work we did was based on the CMIP-5 global climate models, and we used that to drive the 20-kilometer red CM4 regional climate model with 1D lake model. The current work we're doing now that's in process, in progress at this point, is using the new WRF, the 3-kilometer coupled to 3D FVCOM. We're currently downscaling 2 of the CMIP-6 global climate models. That's something that sometime next year we should have output for. During the past year, we spent a lot of time basically having to port the model from one federal supercomputer to another when our grant ended. So that kind of delayed a lot of it. So that's the current work. In terms of, I think at this point, there's not a lot of CMIP-6 dynamical downscaling data sets that are available yet. Those are our group and others are still working on that.
Excellent, thank you.
Yeah.
Looks like we have a question from Ezra. Are the products available online that provide downscaled future climate projections at the county level? Designers and planners would be able to use those kinds of data in their work, they believe.
That is a good question at the county scale. You can get online these MACA and LOCA outputs. You can also get some of these from Minnesota at county scale and watershed scale. We've explored doing that with the UWPD, but it is expensive to do that, and we just haven't had the funds available for us. There is the Wisconsin Rainfall Project that Dan Wright's been leading, and that has county scale projections. I don't think it uses the newer CMIP 6 models though. So when you're specifically getting down to the county scale, it does get harder. But the statewide projections from the newer CMIP 6 models certainly are available. Michael, do you have something? Is it a different story with the RCMs?
I had a question actually back to you again. Sorry. So Dave's CMIP 6 statistical goal downscaling, is that available online at this point, or is it just through contacting Dave?
It's he put the CMIP 5 version. He made that available publicly. I don't
Yeah,
know yet if the CMIP 6 is. We certainly have the maps on the wiki site, but
yeah,
maps alone may not be enough for people's data needs. So we'd have to
yeah.
check with Dave to see if that's been uploaded to a cloud.
Yeah, but in terms of dynamical downscaling, I don't think I've seen any groups that have made specifically county level like average data. Usually it's basically from an original grid, and you got to whether you want to do your analysis within the county. That's the
Mhm.
normal approach.
I've got a couple quick questions, Austin. I can't figure out how to raise my hand, so
Oh, that's okay. Sorry.
call me a Zoom ignorant. Anyway, a real quick definition thing, kind of on behalf of the group. I think I know what this means, but uh, you had described convective parameterization, and I think my understanding is that's because unless the model is very, very detailed, perhaps 3 kilometer, you need to somehow account for thunderstorm type rainfall in a way that's not directly modeled. But could you explain that a little bit?
Yeah, ultimately, when you look at something like a cumulonimbus cloud, a thunderstorm cloud, or some of those features, they occur at like sub-kilometer grid cell. There's no way a regional model or a global model can directly simulate that. Most of the global models are 100 kilometers. Most of the regional models are down to a few kilometers. Um, you need to be able to simulate the large scale rising motion and convergence, individual turbulence within convective clouds, for example, to simulate those heavy rain events. If you run a regional model down to, say, 1 to 3 kilometers, then it's really considered convection permitting. So you're not using the convective parameterization. You might be able to simulate those systems, but if you want convection resolving, you got to go even lower than 1 kilometer, which is pretty much people can't really do much of at this point. When you use convective parameterization, basically the idea is you're trying to estimate, like based on large scale vertical motions and moisture and winds, what kind of cumulus convective clouds you might have occurring and what kind of rainfall rates you might get. So it's using like empirical relationships to infer what should be happening, as opposed to with convection resolving and permitting, where you're directly simulating those intense rising motions and development of unstable atmospheric conditions that give you the heavy rains. So it's difference between like inferring it versus actually directly simulating it.
Okay. Okay, thanks. And so this 3 kilometer work that you described on the Great Lakes, it's a step toward directly modeling convective storms, but maybe it's not all the way there. Is that right?
So without using any parameterization, just it, so you are directly simulating it, but you're not going to get the very fine detailed morphology of individual cumulonimbus clouds or individual features within a squall line. So you can get the basic morphology, but not all the fine details of it. So you're getting pretty close to it. Now there's a pros and cons. So when you run a model, say if you run a model at a couple kilometers, they take so long to run, you can't end up running like a 20-year simulation. So you end up with shorter simulations. So you have maybe a better representation of these extremes, but you have a smaller sample size.
Right.
So that's not necessarily perfect either. But at least we get a better sense about the current issue is that summer rainfall projections and global models are pretty unreliable, largely because they're not directly simulating the actual cause of those heavy rain events, but they're just parameterizing them. So at least we're moving in that direction in terms of better representing those processes that affect those heavy rain events, or which are really our concern in the first place.
Okay, thank you. I'm
Yeah.
looking to see if other people have questions. I do have kind of a general question, and I promise I'll shut up after this. I saw a very interesting NOVA program, right? So what I know I learned on PBS, no, not quite, but it was describing, among other things, the very, the awful sequence of events in the North Carolina storms last year. And there was some kind of a stuck low pressure uh, loop, kind of over Tennessee, and then this hurricane came in, and it was piling upon, bad situations for a lot of rainfall in the east side of the Appalachians. Well, how many times do you see that? I'm thinking about what kind of data do you have on us from a statistical scaling situation? If you don't have observations, how are you going to pull that in? Or is that really the only way to analyze that is dynamical? And I'll leave it at that. It's a broad question.
Well, I think both approaches, Rob, could work for that. Actually, I don't think that the traditional analog approach that Loca and Maca use would do very well with that, because that was pretty much an unprecedented type of rainfall. But the nice thing about the probabilistic downscaling is that it is a PDF, and in theory, a PDF has tails almost forever. So even though it might be infinitesimal chance of a storm like that, it actually happened. And so that is one of the benefits, I would say, of the UWPD methodology. And from my understanding of that event, it wasn't freakish meteorologically, in the sense that it's large scale flow. It was often unusually warm Gulf of Mexico. It was very persistent. And then you had a lot of orographic uplift, and then problems with runoff because of the steepness of the topography in that area. But in terms of the ingredients, I don't think they were so freakish. It was just the duration of the event, the magnitude, all these other factors kind of came together in a tragic way.
It did
But
create a tremendous amount of rainfall, kind of be the hydrology guy. The thing, and oftentimes this is the case, the thing that really produced the big flood was the antecedent moisture. And so they had a soaking rain for several days, and then they just had more. So after a while, the whole world becomes a parking lot. And I think that's what happened there.
yeah, so that's a good example of a compound extreme, where it wasn't just the second heaviest amount. It that was predicated on that being, the antecedent conditions, as you said. So that is something that both RCMs and statistical downscaling can do, even global climate models can do, is capture compound extremes, things that just by chance line up one after the other in a really bad way.
One of that challenge with the statistical downscaling, though, for this scenario is that it's based on the assumption that the global climate model is able to directly simulate that hurricane to a reasonable intensity. And that may be a challenge with the global climate model. Usually, hurricane simulations are not extremely accurate with global models.
Looks like we
I
have a
see somebody.
question
Yeah.
from Andrew. It says, with the 3D model, I think you mentioned something about the churning force or motion related to ice on the rivers. Why might it be important to consider those behaviors when studying climate change? And I think it's
Yes.
probably more related to the lake ice.
Yes. So there's a few features that when you use a 1D lake model, you get too much ice for a few reasons. One reason is that usually lake ice breakup by high wind events is not well represented in a 1D lake model as opposed to a 3D lake model. So that does help in terms of getting a more accurate capturing of the actual total ice cover. It allows for more ice breakup. Then also the motion of the ice on the lakes can redistribute the ice. There was a study, I think, by Dave Wright, in which he looked at how the distribution on ice of the lake, the spatial distribution, can affect the shape or the morphology of the lake effect snow that occurs as a result of it. So a lot of times with the 1D lake model, you end up with ice that's more like kind of focused on the latitude of the lake rather than the depth of the lake. And it's also not very sensitive to features such as the wind in terms of breakup and redistribution. So I think that's one of the keys, getting the absolute amount of ice correct and also getting the morphology of the lake effect snow correct. Um,
I just one more quick question. If you were to look at both these methods and think about the storm that came through in August, both appropriate? Is the dynamical one capture it better? I mean, here in Platteville, we had 5 inches. In Milwaukee, they had 11, right? And so it was something that evolved just over a short span of the width of our state and had really differing impacts and severe consequences in one place and not so severe in the other.
Yeah, I think that that's another case where either approach could work. I mean, certainly the fine scale of a regional climate model is designed for picking up those kind of small scale variations, but so too can the statistical downscaling at high resolution. And we know from the meteorological factors for that storm, not unlike Hurricane Helene down in the Gulf last year, that everything, it was literally the perfect storm. All the conditions were just right. It was extremely humid. We had a stationary front. There's even a small scale mesoscale vortex that rang out even more moisture. So all of those things, even though they aren't explicitly captured by a global climate model, they are functions that go into the PDF of those scale and shape parameters in the precipitation amount. So if you get the right PDF and the probabilities of these freakish foot of rain in Milwaukee, once in a while, about once in 1,000 years, it looks like that'll happen. And so it certainly can be represented. And most likely, as we get more humidity in the warmer atmosphere, the return period will shrink down below 1 in 1,000.
Is
Yeah, I
that,
think that kind of
oops, sorry, go ahead.
for that kind of event, I think that statistical downscaling would perform well. You're not dealing with complex topography. You're not really dealing with soil atmosphere interactions or feedbacks, or like a lake atmosphere interactions or complex topography features. I think in that case, using a dynamical downscaling approach is probably more like almost like an overkill for that kind of thing, in my impression. A lot of why I got into dynamical downscaling is I'm really interested in how the Great Lakes are changing and how the climate around the Great Lakes is sensitive to that changing lake. But when you're looking at, say, like flat Wisconsin by weather features that are really just atmospheric driven large scale phenomena, I mean, there's not really an obvious reason why statistical downscaling wouldn't get the job done.
Yeah, I agree, Michael. One caveat to that, though, is that I think that most of the rainfall that hit the Milwaukee area happened within just a matter of hours. It wasn't even, we call it a 24-hour rainfall, which it is, but most of that, I think, was within about a 6-hour period. And that's something that the dynamical model, the regional climate model, could pick up. Whereas if you look at a daily average from the statistical output, you wouldn't know if it happened in 3 hours or 24 steady hours of rainfall.
Yeah, yeah, yeah. When you're really interested in sub-daily, then there are definitely some limitations with statistical downscaling. I think it's still going to be forced by observations, which include those daily totals. So you'll still get those large magnitudes, but you really can't do any kind of an analysis on any kind of hourly or sub-daily scale. That's why there's not a lot of studies out there that look at what is the future change in 1 hour rain events or 3 hour rain events. People are mainly focused on those daily rain events because the data is just more readily available.
And I noticed that Ezra's provided some helpful links to like the wiki website that has the trends and projections, as well as the county scale retrospective trends in temperature and precipitation, also citing the State Climatology Office website for various data sources. State
Steve,
Cartographer's Office too.
Can I ask you a question?
Sure.
So when you showed the Maca and Loca, and you showed that they were deficient in the extreme rainfall, is that primarily because that they are using an observed database, like I think the LIVNA gridded database, that maybe the gridded data set that goes in from observation is also deficient in the extremes? Is that part of the issue?
I mean, this is a better question for Dave, but I think that they were trained on reanalysis. And so to the extent that reanalysis is underrepresenting those extremes, then they would be affected by it too. The ERA 5 reanalysis is awfully good and pretty fine scale compared to past reanalyses, so it has a fighting chance, but still you're dealing with averaging over a certain area grid box, which will still kind of dilute some of your precip extremes.
Yeah.
Looks like you guys got another question. How much did the urban heat island exacerbate the Milwaukee experience?
Oh, I assume Milwaukee experience being the heavy rainfall.
Yeah.
Boy, It's a good question. I've not heard of it playing a big role, although I don't know if anyone's diagnosed it to that degree. We think of urban heat islands, of course, as affecting temperature more. It was the heavy rainfall did affect more than just the Milwaukee urban area. The 4 counties right around it were all, I think, declared disaster areas. So it did go outside of the urban heat island, but that's not to say that Milwaukee's extra urban heating couldn't have provided an extra oomph to make that storm even stronger.
Was it close to freezing at the time, or do you know what kind of temperatures they had?
Uh, well, this was just in August, so it was warm.
Oh, I'm sorry. Never, I'm sorry. I thought you were talking about the snow event that just happened this past week.
Oh, no, I'm sorry. Oh, so maybe that was the question.
I, I
I don't
might have
know.
been confused. Sorry.
Jacob, which Milwaukee experience was it? The lake effect snowfall or the deluge of rain this summer?
I was thinking of the deluge of rain this summer. I thought it was UT Houston was trying to unwind the urban heat island effect and climate change. They were doing some research, and I, in the context of the question that Austin asked, I've been wondering how much does urban heat island exacerbate the, in particular, precipitation events, large precipitation events, and it's something I thought that there was something. I thought it was UT Houston. I read a paper had published something about last year that it was like a statistically significant impact
Hmm.
in terms of the precipitation effect,
Okay.
but not understanding how far out it ranged. I think your comment, Steve, like how much did the urban heating effect of Milwaukee affect the county? I don't know, but they were finding there was quite a bit of difference between rural areas and urban areas, and the predicted precipitation outcomes predicted precipitation events compared with actual outcomes, and trying to unknit the urban heat island effect as a result of climate change. So maybe it really does exacerbate, and we don't quite understand how and when it will exacerbate.
Yeah, it's true. This is a question that's been studied for a long time, is what effect urban regions have on precipitation. It could be through heating, as you're pointing out, and it could also be, as people have speculated before, about emissions, pollutants, aerosols affecting cloud condensation and therefore rain processes within clouds and ultimately precipitation. So there's a variety of ways that urban regions could. And whether Milwaukee's big enough, urban enough, and so on, compared to say Houston or New York, Los Angeles, I don't know. But Milwaukee is a tricky one because it's bordering right next to Lake Michigan, a very different type of land surface. But yeah, I would be interested in hearing more about that study to see what they unraveled.
So just kind of maybe if there's other questions, we'll take a few more. But I got one last one. So the statistically downscaled, the UWPD stuff, that is on CMIP 6. And what level, what resolution is it downscaled to? And is that available on servers for people to grab or not?
Yeah, so that was the question earlier, is whether the newer output is available for everyone. I don't know. I'll have to check with Dave. In terms of resolution, it's on the order of 10 kilometers or less, 8 kilometers. Do you remember exactly, Michael? I know it's somewhere around that.
I think he usually just has the 0.1 degree, right, which is about 8 to 10 kilometers. I think he's always used the same resolution for all versions of this downscaling.
Great.
Yeah, so if you're used to global resolution, that sounds great. If you're trying to deal with convective thunderstorms, it's not quite enough. Ezra just sent me a note here asking about the availability of that Minnesota data. I offhand, Ezra, I'd have to kind of Google it, but I think it's what's it called? Minnesota. It's through the Minnesota DNR, I believe. I think you'd have to just find the right Google combination to come up with it. Maybe Explorer is in the name. Climate Explorer, I want to say.
There's a Minnesota Climate Explorer.
Yeah,
That's right.
that's,
When I
think that's
Googled it, that's what I see. Yeah.
Yeah, I think that's the one. And it has
Uh-huh.
different options, county scale, watershed scale, and so forth.
Yeah.
Are you able to put that in the chat? Oh, there we go. Looks like Ezra found it.
Yeah, Minnesota also has a useful publication on understanding downscaling.
Mm.
Well, great. Thank you, Steve. Thank you, Michael. I think, we appreciate your time. It was a great talk. I definitely learned things that I did not know, especially in terms of what's going on locally, especially with the UWPD stuff. That's really neat. I think those of you that are attending, again, if you're looking for PDHs, make sure you go to the link that I posted in the chat at the beginning, the or Google Platteville Climate Resiliency Seminar Series, and make sure you click on the PDH button. And if you've got ideas or topics that you want to hear about, feel free to email me. We're trying to do these once every 2 to 3 months. So we've got some topic areas, feedback from the infrastructure group, and this was definitely one of the high demand talks. We definitely appreciate you, Steve, and you, Michael, for being able to do this.
Me too, Austin. Thank you. Glad to see so many people attended today.
Yeah. Thank you, Austin.
Yeah. I will stop the recording. If people want to, if there's any other questions, maybe we'll hang on for